to 8%. Could be in the range from 4 to 8% ash content. Torrefaction doesn't remove the ash, just a limited amount, and washing remove a little bit, but you have to add any additive to increase a little bit ash content. Organ?
I think it's still a field where a lot of learning and differentiation can be made. So when speaking about ash content, we can speak about different elements that can be reduced, and each of them react a bit differently to the solutions, if it's pure water, if it's anything added to it or not, and especially to the temperature of the washing. Mm-hmm. So I can report about several different types of feedstock, and each of them have reacted quite differently. We can see it already in the lab, but also on large scale. And it's really a matter of how much effort do you want to spend on it? And that's an economic question. That's quite typical because, like in other cases, it's a design question to say what process effort can be taken to obtain a certain goal. And if the goal is reducing 20% of the ash content, you can achieve it. If the goal is obtaining 40% of the ash content, you can also obtain it at a higher cost. So that was our experience, simply depending on the parameters for the washing, you can obtain different results. And so it's a typical engineering task for defining such a project to say what effort do we want to take, or do we need to take to obtain a certain ash reduction goal.
And I think one of the challenges with taking that effort is how consistent does the biomass feedstock remain over time. And we did a large study with the National Corn Growers Association where we collected large amounts of corn stover, and over just a period of weeks, the degradation of that material, the increase in ash content radically changed that. And we had another project I worked on in the 90s where we designed an entire process around using oat hulls, very light, very hard to handle. And ultimately, by the time we'd finished designing and permitting that process, General Mills, who produced those oat hulls, found another use for them. And so I think the combination of the economic challenge that Wolfgang spoke to, coupled with the security of supply and the variability of that supply, make agricultural inputs a more challenging input.
But the great thing is, and I think that's a common experience now to all of us here, the general idea of torrefaction is that you can add resources to the energy market, which otherwise, without this technology, simply wouldn't go there. And I think this whole washing topic is a real breakthrough for agricultural biomass, because this has always been one of the most difficult feed materials. And now being able to combine such pre-treatment methods with torrefaction really opens a very huge field of feed materials that are available.
And we have to take into account also that we have millions of tons of coal or pet fuels, fossil fuels, being used at present in different sectors. And torrefied biomass is a pretty drop-in fuel, biofuel, to replace these fuels. We are talking about 1 million tons every. In the case of Spain, we are talking about 4 million ton oil equivalent. Demand by the energy sector is 3, 4, 5 times higher in Europe.
Well, certainly yes, and that's one of the questions. How can you scale up production? How can you scale up production of torrefied biomass such that it becomes a real useful replacement for these millions of tons? And I think especially when being able to turn to agricultural resources, it's easier for many to understand that such quantities are available. If you speak about wood chips, then everybody who knows about this market would soon say, okay, that's a problem to provide so many millions of tons from the forests. But now that you can open this door and take all those huge amounts of agricultural residues in consideration, I think that's a real game changer. So I think it's very good to have a discussion like this today and to make this topic known to as many people as possible.
Yeah, I would say that it's also important to add always, in the case of agricultural biomass, but also woody biomass as well, the word residues. Because then at the end of the day, we are giving a value added to something that otherwise will be landfill or is just wasted, you know, and we can make energy out of it, which is necessarily for the decarbonization of our continent and the entire world, I would say. So in this sense, I think that using also agricultural residues for energy production could alleviate some of the critics that sometimes we have in the biomass sector when using wood, because then when we talk about the forest, etc., there is a lot of controversy around it. But I think it's easy to understand for everyone that there are a lot of residues produced from agricultural products. There is a challenge to utilize this, but there is where torrefaction can be of added value. And also, I would like to finish that I hope this is not a monologue from the speakers. So please, if we are really in a small group, if anyone wants to talk, like really, this is the time to unmute yourself. If not possible for you, ask to me on the chat and I will give you the possibility to unmute. So take this opportunity to bombard with questions to the speakers.
While we wait for that question, I will piggyback on Christina's comment that I think there's an added element that is interesting around the agricultural residues, which is the very short life cycle that these are annually reproduced. And I think there's an opportunity to take advantage of that in an LCA that maybe hasn't been done today, or I haven't seen one done today, but that I think is a selling point again beyond sort of the wood pellet technology that's out there today.
And James, again, I'd like to add something, because this fast rotation is definitely an extremely interesting feature. And it's today also one of the obstacles, because in many cases, those residuals are fast degrading. We know this, for example, from bagasse, the remainders from sugarcane. They lose about 30% of their energy content within the first 2 months of storage. And this goes down to more than 50% after a while. And that's, again, one of these great things. If you can capture this value, which otherwise simply disappears into degradation, if you can capture this value at an early stage through torrefaction technology, then it's more than obvious that here is a added value in it.
Thanks, Wolfgang. Jean-Marc, do you have a question?
Yeah, it's yeah. I mean, I see the torrefaction as an opportunity to harmonize the fuel quality, starting from many different feedstocks as agricultural residues. But I also see that there is a kind of progressive kind of torrefaction pyrolysis carbonization process depending on the temperature and the carbonization and the length of the reaction probably. So yeah, is this really the main advantage to harmonize the fuel quality? And in that case, isn't it making sense to go quite deep in the carbonization process to have a kind of harmonized fuel? And something that was not mentioned also before, the hydrophobicity. I mean, can we finally store this fuel outside? And coming back to my first point, the ash content. We don't remove the ashes. So it means that the main difference among these different fuels could still depends on the ash content in reality. And the ash and the ash melting temperature will still be a problem in the boiler at the end, except if the ash with the washing. But but so the question is, how far do we harmonize the different quality to reach homogeneous fuel, and how far do we reach hydrophobicity? Thank you.
Many questions in one. Okay. Step by step. There is a point, an optimum point regarding carbonization degree. Okay, and it's been depending on the business case. So, and depends on how, for example, higher the heating value, the lower the logistic cost. So, depending on how is your logistic distance or your transport distance, it could be changed. Okay, it's not the same to bring pellets overseas from USA or from South America to Europe than internal transport in Europe. Okay, this is one point. Second, the higher the carbonization degree, the lower the energy efficiency. So less energy you have in the end product from the total energy input to the process, and that affects the heating, the LCA emissions, and affects also the product cost. So there is an optimum, and this is depends on the end use, depending on the logistics. It is an optimum in the heating value. Then, if you increase much the heating value, you could have some problems with pelletization stage. So this also to take into account, or you have to use additives, okay, for the pelletization step. Okay, and regarding the ash behavior, okay, chlorine is affected by torrefaction or organic blended chlorine. And in the other elements like potassium and so on, is why this is the reason why we are working on combining torrefaction with other processes. There are synergic effects in the combination. This is important. It's not just to sum up some processes. It's the combination in a smart way. You have synergies, and it's in order to get the standardized fuel with better performance. Regarding ash content, as mentioned in a previous question, it's difficult to change this. You can work on that a little bit, but it depends on the original ash content of the feedstock.
Michael Wild, may I just come in on what Javier said here? It's true that if you go in higher carbonization, we have a lower efficiency if we would look only on the solids that are traded. But the overall system efficiency may even increase. And from the point of view that we are under jeopardy in Europe now using imported biomass, I think it is a very, very strong argument that we are not consuming or exporting all of the biomass from the places of origin, Southeast USA, South America, or whatsoever, but we create also value there. We create value because the gas can be turned either into steam, producing electricity, or gas fueling any jet engines, or other ways, turning it into cooling and then offering cooling capacity, cool warehouses in Africa. So we may, with this technology, I think, or use this technology also as an argument in the sustainability debate and into the debate about international trade and transfer of biomasses.
Thanks. I see some questions in the chat. Do you want to take them, Wolfgang? Okay.
Yes, please. Thank you. Very interesting question about India. And Henri-Jean, you mentioned rice straw and large amounts of it being burned in India in the fields, which creates a quite obvious problems during the harvesting seasons, and we know from many cities the smoggy pictures which come really from those rice fields burning the paddy after harvest. And we have started communication with several interested parties in India 2 years ago. NTPC, one of the main energy companies in India with coal fire stations, has started a program to co-fire pellets made from rice straw, but they come exactly to this point that you mentioned here. It's limited by 5 to 10% due to the properties of those rice straw. And it's exactly one of the motivators for this discussion here to say what needs to be done to this feed material prior to torrefaction, such that we can influence these ash properties in a suitable way. And that's how we came into this discussion of washing, screening, other pre-treatment methods. It's at the stage of the harvested feed material where you can influence this type of property. Again, with the goal in the end to achieve a high calorific fuel, which is as close as possible to fossil coal as it is used today, which is as standardized or as homogenized as possible. So I can only give this general comment here. Yes, that's exactly underway, and combining this washing step with the subsequent drying and torrefaction yields a quite surprising increase in quality or better suitability for the specifications of the coal consumers.
But if I dare to add something, why not to add oxygen in the system, pure oxygen at over 1000 centigrade? And you know, there is a French, an unknown French chemist known as Boudoir, Octave Boudoir. He was working in 1905, so he's dead since a long number of time. And he explained that when you increase the temperature above 800 to 1000 centigrade, all you get is only CO. And when you add oxygen on the carbon containing system, you have only CO and H2. And using a gas, syngas with the pure CO and H2 and no tar, nothing, only pure gas, you get a high yield in H2 or CH4 or liquids. It's a real completely innovative approach, much more simple, and you are able to store the CH4, and I see James Menel approving the thing, so that you can store the thing all year, and your unit will be working all year at full capacity. In France, we have over 8,000 megawatt installations of power for heat for wood to heat installation. And this is the installation of 7,000 units. They are operated at 32% of the capacity. It's become, the French are losing money. We don't want to earn money. You know, in French, we are very virtuous Christians, so that the units are run between 13 and 45%. While if you switch to gasifications with a huge network which exists, over 500 terawatt hour capacity, you can run it all year long without any need to wait for the need for heat to make it run. That's it. And that's missing, I think, in these very interesting exchanges, that to use the gasification, full gasification, all year. Condensing the particles of carbons, to use the fact they are minute small parts, to use their high reactivity, which is due to the surface to volume conditions. With oxygen, you get immediate reactions, CO and H2.
I think it's a very interesting pathway that we've spent a lot of time evaluating. And I think one of the challenges and scale of that is just the mass energy balance to achieve 1,000 degrees centigrade, and then ultimately what end market are you taking the product to? And here we focus a lot on energy generation and understand the concept you're outlining for that component. we also look at taking carbon to markets where carbon is still required. So as a water purification ingredient, it's an activated carbon, or in steel making, where it's a necessary element beyond just reduction principles. And so I think it's a part of the solution as well, what you're suggesting, but there's a complex energy balance to get to the right value prop to make call it a CO hydrogen pathway feasible.
We have a couple of questions from another participant, Clara Mendoza. I will put the questions forward, but of course, Clara, you can unmute yourself and add whatever you find. So she's asking, what is your opinion about the extraction of compounds such as hemicellulose before the thermal treatment? Is there any market for those? Is economically attractive?
Hemicellulose is the main compounds that are removed thermally by torrefaction. The emissions of the compounds derived from hemicellulose are connected with the properties of the final product torrefaction. Okay, if you remove in advance hemicellulose, you will have to dry the product before torrefaction, and the product will be by far less reactive than the original one. Okay, there is no real up to now, as far as I know, there is no real market for hemicellulose products. There are a lot of developments in this field to produce products from furfural, from hemicellulose. And you can also go via fermentation of these sugars, but there is no real market now. I think it's a low TRL level, the development. So I don't see any business case in this approach by now.
Moreover, let me add also some thoughts on this question. I think one of the nice things or the charming things about torrefaction is that it's a relatively simple process, suitable for real large-scale application. The more we go into decomposing certain compositions of feed material or of torrefaction gas, the more we get dependent on exact mixture, on exact composition of the input material. So I believe for the purpose of adding a large-scale production flow to the energy market, I think it's an advantage that we don't start going into this fine chemistry of decomposing all those things, but really focus on the main mass and energy flow and apply a quite robust system of heat in an inert atmosphere, of oxidizing the torrefaction gas, of not trying to add too many finely balanced second or third processes on top of it. So I strongly believe that as long as we have a focus on mass production, the whole process should be really as simple as possible and really focus on the main purpose and not start decomposing the ingredients too much.
Wolfgang, that's very practical. And I have to admit, we would go into our lab and our scientists would always have a fractionation column. We'd say, put that away. We're trying to get to an economic pathway to produce these products. So I think there are the opportunities to take things to higher value or specialty, compounds, whether it's extraction of a green acetic acid or furfural or other potential attributes. But I agree very much with your point that if you're looking to penetrate large scalable addressable markets like energy and metallics, that there's an inherent necessity to focus on large scale commercial production, which doesn't have 200 bells and whistles of a research laboratory, right?
And just think about, and Clara, you had a second question also in the chat, working with coffee residues and the seasonality allows only for certain times of the year receiving this kind of input. In such a case, when we see a project case like this, we try to find out, are there any complements during other times of the year? Or are there any other types of feedstock that can be stored for a while without too much degradation so that you get over the year? Which means a torrefaction system is most likely to be not focused on just one type of feed material, but maybe you would always have to be able to handle 2 or 3 different types of feed material over the year. And this even more explains why we think focusing on this very simple main process flow would be a good idea, because when you optimize a system now for extracting certain elements for one type of feed material, you would certainly have a different situation for the other type of feed material later on. And so I think it's definitely a big topic to see how can you make sure feed material supply throughout the year. The main possibilities are either you can create storage for the feed material. If you can harvest only one time in the year and it's dry feed material, then storage would be an option. Large scale operation, of course, but still an option. And the other option would be to use a variety of different feedstock which may still be available for different times of the year, combined with storage options. This should make for a good all-year utilization of an industrial facility. May I just pick up the next question from Jean-Marc? How flexible is the technology? Can it switch from torrefaction depending on market need? In principle, yes, on both ends. It can switch from different types of feed material to the other, and it can also switch to different types of torrefaction degrees or carbonization degree on the output side. However, it's a matter of optimization. So if we need to optimize for, if we want to optimize for one specific type of input and one specific type of output, then of course we will lose efficiency in the overall process when we switch to different inputs and outputs. If we know in time, which means during the engineering phase, that we will have to produce 2 or 3 different types of output, and that we have to use 2 or 3 different types of input material, then it can be properly planned, and then you can work for 2 months on the one material and for the rest of the year on the other type of material, or even switching the process parameters is a matter of a few hours typically in such a facility, if you know what to do and if the dimensions of all equipment are engineered such that it can be processed. James, any comment from your side?
I guess I would agree with everything you said, Wolfgang, and that one of the things we think is advantageous about high temperature torrefaction is that we can take a broader range of feedstocks to a more consistent carbon product, because ultimately we're reducing it to a pretty predominantly carbon end product embodiment. And we've been able to utilize the same commercial scale technology to make everything from water purification activated carbons to agricultural carbons that are holding a very specific biological substrate, to carbons that are used in energy generation, to carbons that are used in electric arc furnaces. So, it's certainly feasible, but I agree with your comments on economic optimization around a product stream, that versatility is a great thing to have. But in terms of large scale, large volume production, you certainly want to optimize around that particular product stream and feedstock streams.
Yeah, I think that was one of the points that Michael addressed during his presentation as well, that there is not the best technology or the best temperature or whatever, you know, it all depends on your input and the output that you want to achieve and the application of the final product as well. So this is something that we want to stress more and more, because during years we have been hearing a lot of people asking like, okay, but what is the best technology? Because there is like a large variety, and I'm sure that there's one and a single one that will succeed, you know. Then with time we realize that it is not like this, because everyone is offering like different conditions and for different applications. I see another question on the chat. Going to carbonization, and which fixed carbon it starts to be problematic with the transport.
And maybe two things that the question's getting at. One would be the potential for self-heating propensities, and the second would just be the bulk density component. I think with regard to the first set of properties, the right combination of time, temperature, and chemistry can, at various carbonization levels, can create a thermally stable product that doesn't have self-heating properties. It's really a matter of, do you cook it right? I think is probably the best way to describe it. With regard to transportation, certainly as you decarbonize the material to a higher degree, the bulk density goes down, and that's where it becomes essential to go to densification technology to allow the product to be transported in a cost-effective manner.
And let me also add the size factor. So typically when it comes to small particles and dust, we do have restrictions in transport, because then we get into explosion risk. But for larger pieces, and this means anything like pellets or briquettes, when it's properly cooled, the material, then we don't see a relevant risk. So cooling is certainly one of the techniques that needs to be applied properly, so that you can be sure that you don't have any heat elements remaining in the end product. But after densification, it typically doesn't take place, because then you have really mixed up everything in such a way that you don't get any. But if for loose material, we have to go through very proper cooling chain to make sure that no remaining glowing elements are anywhere in the overall product.
We have a couple of the moderators of the other room discussions joining us, so I assume that the discussion in the other rooms has ended, right? Yep.
Yes, that's right. That's right. I think
Good.
both other rooms have stopped their activity, so this is the only room still continuing.
Open. Okay, but that's good. More questions from the participants. We still have 16 participants in this room.
I'd like to come back on the rice straw gasifications. Could I get some comment from the panel on this, because there was no reaction, and it's a matter of 800 million tons per year, of which over 100 million in India. Only 10 million are being eaten by sacred cows. And it's a real problem. If you go to Egypt, it's all, when you land in Egypt, in Cairo, it's fumes, and fumes, as Wolfram quoted for India. It's a real stuff. And if Michael Wild want to promote the torrefaction gasification system, and when there is the silica content, it's a major event with a 12% silica on the rice straw. You can't use it to burn it. It's impossible. You make glass, you destroy your furnaces. So the only way to make money with the rice straw is to gasify. And nobody up to now I've heard in this very interesting panel have spoken of gasification of the black carbon thinly in thin parts, so that is highly reactive. and as I said a few minutes ago, over 1000 centigrade, all you get is CO plus H2, highly diversified pure gas mix, no pollutant, from which you get whatever you want in H2, CH4, and liquids. I put the question. 800 million, and whoever wants to save the world, you know, CO2, blah, 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 features, climate, 800 million tons. Here and now.
I'm booking my trip to India now.
It's fact of life. What can I say?
No, but
it's a huge.
But
yes,
basically, when I first stumbled across rice straw, which was in the early 90s in Thailand, I know that the rice mills, they made good money from burning the rice straw and then taking the silica out from the grate and selling it to the glass industry, which obviously was good business at that time because the rice straw would have otherwise cost them money to get rid of. But I mean, in this webinar, but basically also in the Torrefaction Council, we are focusing just on the thermal treatment and not so much on the gas side or on the gasification. But what this I tried also to bring up during my presentation is torrefaction can be seen also as an interim step in the production process, where torrefaction is helping to homogenize and to compact materials like rice straw, and then supply it to maybe even large-scale overseas gasification units, which would be then closer to the customers, because the gas might be more difficult to be transported to customers than it is the solid matter. And so there is a lot of eventual value chains that need to be developed in which torrefaction and the thermal pretreatment may actually really solve the issues which have prevented up to date that gasification of biomass was economically very successful. And so this, I would approach it from that angle and say, okay, there is now agricultural biomass. We know there are certain issues with this. Some of the issues can be solved through torrefication. Other issues might be addressed by pre and post washing. And then we have an interim material, which might be an ideal input material for gasification, or a number of other processes to come and to be developed.
Yes, but I think in this particular example of rice straw, it is not easy because the issue is this fine silica, and well, how to get rid of that is not so easy.
But silica is solid. You just
Sorry?
Silica is a solid. You must be able to get it. Does it go in the gas, or you can't?
No, but it is in rice straw. I mean, it's a solid, but it's not like sand. I mean, it's not present in large clusters or large particles. It's very finely distributed in the rice straw. So that makes it very difficult to extract it.
Well, I've seen photographs, micro photographs TNO is able to do very easily. You see the silica attached to the cellulose is C6 cellulose is not hemicellulose. So if you split rice straw, with some formic acid, you get rid of you dissolve the hydrogen bonding of the lignin and hemicelluloses on one side. You get pure cellulose, and you see silica is concentrated only on the C6 cellulose. So it looks whatever, due to the acid basic function, it must be able to detach it, don't you?
Yeah, of course. Yeah, of course. That triggers the issue that I mean, energy applications are not the only applications for agricultural residues. So there are also other pathways that might be attractive. And one of them is let's say, fractionation in sugars and lignin, and then going that route. And indeed, perhaps for rice straw, that is a more attractive route to follow than via torrefaction go to energy applications.
Okay, so I'd be happy after the speech to talk to you with the Yapkil. I send you email on that stuff.
Yeah, that's good. Yeah, that's fine.
Okay. So you get my name and I can see you. Okay, and Michael will laugh. Okay.
You wanted to say something as well, Wolfgang?
I'm afraid I'm again adding a very pragmatic comment here. The whole torrefaction industry is on a developing path. So it's about first large-scale commercial lines being rolled out right now. It's a necessity for all developers of torrefaction systems now to really focus on low-hanging fruit. So in any case, we will have a favor for easier to handle material than the more complex materials. And this comes quite naturally in all our investigations and test runs. We can understand how to deal with this or with that material, also what is more attractive to end customers in what type of applications. And by the way, there has been a strong increase in requests from gasifying systems. So we are quite aware that torrefied product, like Michael mentioned, as an interim product for gasification can be a very attractive niche. But having said all of that, if a feed material is very complex to handle or the end product is very complex to handle, there will be, for the time being, a preference to easier to handle materials, and there are a lot of them.
So thank you, Jan. Wolfgang, I don't see more questions on the chat. So I think the discussion is about to end. I think that we achieved the purpose of this webinar. So we definitely went very detailed in this in the discussions in these breakout rooms, talking about chemistry and many things that I was even lost myself many times. So I'm sure that the discussion was really detailed and interesting, and also the networking opportunities. So I'm glad that some of the participants will contact the speakers afterwards, and remember that IBTC can always serve as a contact point. So if you want to address privately any of the speakers, do not hesitate to contact IBTC, and we will put you in contact with the speakers and any other of the IBTC members. With this, Michael, I don't know if you want to add something besides thanking, of course, all the participants.
And World Biomass Association as well to co-organize this. Very, very, very nice to see, and the big interest of audience. And I think we will try to keep this format and see if it's continued to be a success. Thank you to all of the speakers and our panelists as well. And by this, I hope that eventually we have in the future also members with a gasification background in IBTC. Okay, by this, thank you very much, and enjoy your evening. Bye-bye.
Thanks, Michael. Thanks, Christina. Bye.
Thanks to all. Bye-bye.